Hey guys, I'm recording this video for you the night before. It looks like I may not be there tomorrow, being today the day that you actually hear this. But it's important that you go through the lesson, and when I come back, we will be reviewing for a quiz that contains 5.3. So please make sure you're going along. Pause it when necessary. Because I'm going to be going through it just as if you could stop this at any time, since I'm not going to be doing this in person there. So you can slow it down. You can re-listen to anything you want. So Chapter 5, Section 3 is using angle bisectors of triangles. So yesterday we talked about perpendicular bisectors. Today is angle bisectors. So we're not going to be talking about lines being bisected today. We're talking about angles being bisected. So this is the angle bisector theorem, and it says if a point is on the angle bisector of an angle, then it is equidistant from the two sides of the angle. So what we're looking at here is AD, this line right here, is definitely the angle bisector, and I can tell that because you can see that this angle is being bisected. Therefore, ray AD, that red line that's going there, is definitely the angle bisector. So it says if a point is on the bisector of an angle, so like look at point D. Since point D is on the angle bisector, then it is equidistant from the two sides of the angle. So here are the two sides of the angle right here. Here's one side of the angle, a second side. So what they're saying is that red dot is equidistant from the sides. Now check it out. It's going to go directly to the sides. So that's why we have this 90-degree angle right there. We talked about this before in an earlier lesson, I think maybe back in chapter 2, where we said the shortest distance to get to that side is to go directly to it. So we're going to walk perpendicularly towards it. Basically what that little 90 degrees is showing us there, it's the shortest distance from D to that side AC right there. That's what it gets from us. Like showing that it's perpendicular there shows it's the shortest possible path. Same thing on the other side there. We can see that there is this line DB. It's going from the point right there, the point that is on the angle bisector, and it's going directly to the side. That's what that 90 degrees gives us there, that it's the shortest path there. So I know that it's definitely the shortest path on both. Well, then that point is equidistant from the sides, meaning that this distance right here is exactly the same as that distance right there, as long as it's on the angle bisector. You see an angle bisector? Here's our angle bisector. Then any point on here is equidistant from the sides. So kind of similar to what we did yesterday, that we said if it was on the perpendicular bisector, then it's equidistant from the endpoints. But now we're saying if it's on an angle bisector, it's equidistant from the sides. Basically what we get from that is this piece here is congruent to that piece there if this point is on the angle bisector, and it is. We can see that. We see this is the angle bisector because I see an angle being bisected. All right, so just like we had the perpendicular bisector theorem, and it was followed by the converse of the perpendicular bisector theorem, well, we just had the angle bisector theorem, and now we have the converse of the angle bisector theorem. And it says that if a point is in the interior of an angle, all it means is that here is the interior of an angle, like Pac-Man's mouth. Imagine that red thing is like Pac-Man's mouth there, and inside right there, there's a point that is in the interior of an angle, and it is equidistant from the sides of an angle. Since I see there that it's marked as being equidistant from the sides, well, then that means that the reason that happened is because it must be on the bisector of an angle right there. So the earlier one, the one we just did, said that if it's on the angle bisector, then it's equidistant from the sides. Now we're looking at it and we say, hey, it's equidistant from the sides. So guess what? It must be on the angle bisector, meaning that these two angles right here are congruent. It gives us that piece of information there. So you could take a look at that, and it says that if like we've got these two pieces here that are congruent, then it means that those two angles here and here must be congruent because it's the angle bisector. Okay, we talked about this word concurrency. Remember, concurrency is like three or more lines meeting up at the same spot. The concurrency of the angle bisectors. Yesterday we had the concurrency of the perpendicular bisectors. Today the angle bisectors are going to meet up at a point. The angle bisectors of a triangle intersect at a point that is equidistant from the sides of the triangle. So check it out. Angle bisectors. Now you're going to have to draw this in here because this is a piece of information. Angle bisectors. So here is an angle bisector. Now we'd have to give this to you. This piece of information is not something I would just know unless I said, like, if I already told you that AP was an angle bisector, that would be acceptable. Or I'd have to give you this piece of information, that those two angles are being bisected. These two angles are being bisected, and these two angles are being bisected up here. If they are being bisected, that makes these red lines angle bisectors. Now those angle bisectors are going to go and they're just going to run towards the middle of the triangle, and they run and they hit this point of concurrency, which does have a name. Remember, we had the circumcenter was the name for where the perpendicular bisectors meet up. These are the angle bisectors that are meeting up, and they meet up at this point right here. And this point is equidistant from the sides of the triangle. So now I'm going to go directly to the sides. I'm not going to the vertex this time. Remember, the circumcenter was equidistant from the vertices. Here, this point, I'm going to go directly to the side. So boom, forms a 90-degree angle. Why? Because it's the shortest possible distance. So there is one line going directly to the sides. Boom, directly to another side there. Bam, directly to a side right there. What it is those three lines there are definitely going to be congruent. And this happens when the three angle bisectors come together, that point of concurrency there, that point is equidistant from the sides. But that point was created by using the angle bisectors. The angle bisectors came together, and they come together at this point, which we'll talk about its name in just a minute. But right now, the angle bisectors came together. It comes together at that point P, that blue dot there, and that dot is equidistant from the sides. Now again, this is the part that yesterday a lot of people took some time to go, oh wait, what? Let me hear that a couple times. So if you need to watch this over again, this is the slide that you might want to invest some time in, because this is the one that's different from yesterday, but it still can be a little confusing until you watch it a couple times and go, oh, okay, so it was made from the angle bisectors. All those red lines came together. Those are angle bisectors. They all came together at point P. That is a point of concurrency. That point is equidistant from the sides, meaning see all those green lines coming from the blue point P? All of those are congruent to each other. So that point that we were just talking about is called the incenter. Now notice this time, it is not a circle that goes around the triangle. This is a circle that goes in the triangle. The incenter is a circle that is in the triangle. So it is the point of concurrency of the three angle bisectors. Remember, look at this picture here. See those red lines? They are angle bisectors. You can tell by looking at the corners. And each corner, there's an angle that is being bisected. And they're all running together. And where they come together is a point of concurrency. That point of concurrency right here is called the incenter. The incenter is equidistant from the sides of the triangle. So if I go directly from that point to each individual side, it would show me that these lines. Now notice I'm even drawing lines in here. That's because those lines may not be shown, but it doesn't mean that it's not equidistant from the sides, meaning this piece, congruent to this piece, congruent to that piece. It does not mean the red lines are congruent to each other. That was yesterday. That's when we have the perpendicular bisectors come together. Where they meet up is equidistant. That point is equidistant from the vertices of the triangle. These red lines here, all they are there to do is to split up those angles. This circle is said to be inscribed. It is a circle that is inscribed within the triangle. The triangle that we did yesterday, the one that had the triangle on the outside, we'd say was circumscribed by that circle. Like it is a circle that surrounds it. So inscribed, the circle is inside. If you're like, what's the difference between the two? Inscribed means circle is inside. Okay, so for the next few exercises, we're going to find the value of x. So some of these are going to go pretty quickly. Notice here that I'm trying to find the value of x. I see 27 degrees, 27 degrees. That makes this an angle bisector. And what we learned from the angle bisector theorem is it says that if there is a point, like that point right there, that is on the angle bisector, then it is equidistant from the sides, meaning this is congruent to that, or x is equal to 15. That's all there is, straightforward for that. Quick one. That is the angle bisector theorem. Angle bisector theorem. Okay, next up. I do not know that these angles are being bisected. I'm going to draw something in that's not necessarily true. I cannot say this from the beginning. I don't know that. But what I do know is this. By looking at the picture, I can see that this line right here, let me use a different color. This line right here is equidistant to this line right there. Since this point right here, let me change colors one more time. This point right here is equidistant from the sides. It means that it must be on the angle bisector. This is the converse of the angle bisector theorem. It says that since that yellow point there is equidistant from the sides, it must lie on the angle bisectors, meaning this piece over here, congruent to that piece right there. Or 4x minus 6 is equal to 3x plus 5. I know those numbers are a little bit hard to read there. In which case I will subtract 3x from both sides, and I get x minus 6 is equal to 5. Add 6 to both sides, and I get x is equal to 11. Now it said to find the value of x. If I needed to figure out what those angles were, I would just plug in. So in this case, the top one would be 3 times 11 plus 5. That would be 38 degrees. On the bottom, we get 44 minus 6. That would be 38 degrees. It checks out. So even though it just asked me for the value of x, if I needed to find those angles in there, I could just plug in. Last but not least, I see that this is the angle bisector. I notice that because that angle is being bisected. Because it is being bisected, then this point is on the angle bisector. Therefore, it will always, always, always be equidistant from the sides. So, meaning those two pieces will definitely be congruent to each other. So 6x minus 5 will be equal to 5x. Let's add 5 to both sides, and we get 6x is equal to 5x plus 5. Let's subtract 5x from both sides, and we get x is equal to 5. We found the value of x, but let's say you had to figure out a certain piece, just plug it in wherever. This would be 5 times 5 is 25. This would be 6 times 5 is 30, minus 5 would be 25, so it still checks out. So short lesson, hopefully this wasn't too bad. The key takeaways here are this is the angle bisector theorem we're talking about. So if you already know that it's an angle bisector, if you can already see the bisected angle, then you're going to use the angle bisector theorem. But if you're not sure the angles are the same, but you can see that you are equidistant from the sides, then you're going to use the converse of the angle bisector theorem. And the only other thing to notice there is that where the angle bisectors meet up in a triangle, that point of concurrency is called the incenter. The incenter is equidistant from the sides. So again, if you have not started little note cards, we're going to be quizzing 5-1 to 5-3 on Thursday. So you've got this for homework, and you're going to have the reviews for homework. So just make sure you're going over these because there's a lot to take a look at. All right. Hopefully everything will go well. We will be able to talk about this lesson when I return.